Okay, Gabby, this is going to be part two. I apologize in advance. This one's going to be a little longer. You can stop it and break it into little segments. So I have to go back, and before I talk about the Doppler effect, I got to talk about two properties of waves. Um, One called frequency, and the other called amplitude, which are things you talked about before, again, back in the wave chapter. But especially frequency is really important for this understanding about the Doppler effect. So it gets a little confusing, but because sound is a longitudinal wave, it's a pressure wave. So we have compressions and rarefactions as this longitudinal wave propagates in this, from one person's mouth to another person's ear. What you're really doing is you're changing the pressure in the air. Now, it turns out it's really inconvenient to draw pressure waves, longitudinal waves. So it's much easier to actually take a look at the pressure of that air or that medium and to turn it into a picture that's more familiar. So just be careful. Sound is still longitudinal, and it looks like this, but it's a lot easier to do the following. We take any area that's a compressed air where the air is close together, the molecules are close together, and we call that a compression, and we say it's got high pressure, there's a high density here. In areas where it's rarefied, we say the density is really low, so the pressure is really low. So in this way, we can take this really difficult thing to draw, this longitudinal wave, and we can draw it as a more familiar sine wave. Now, just be careful. It's not what we're saying is it's not it looks like a transverse wave. It's not transverse. We're plotting it so it looks transverse. And now we can talk about, hey, the frequency or the wavelength. We can use the same vocabulary as before. So from now on, when I draw a sound wave, even though it's really this, we're going to draw it like this. We're going to draw it as a pressure wave. It just makes it much easier when we're doing problems. So the key note here, if you're taking down a couple notes, the key note is when we talk about the frequency of a wave, that frequency is a property of the wave, but how it manifests or how it shows up as a perception by a human being, we call it pitch. So frequency is a wave property, but we perceive it as a pitch or a note. So for example, if we look at this, let's assume this represents 1 second. We're saying this wave has a frequency of 1, 2, 3, 4, 5, 6 cycles per second. We call this 6 hertz, or 6 waves per second. We say it's a relatively high frequency. If I go to something, if this is also a second, we can say this has a frequency of 1, 2, 3 complete waves. This has a lower frequency. So a higher frequency has a higher note. Now, I apologize in advance. I'm going to sing again. So the high frequency might be something like oh, and the low frequency might be oh. And again, those were really bad. Now, you may recall, the other thing is that humans can't hear every frequency. So I'll get that in a second. So high frequency means high note or high pitch. Low frequency means low note or low pitch. Now, this is kind of a little factoid. I'm not sure if you really need to know it, but most human beings can hear waves with a frequency between 20 hertz. So if something oscillates 20 times per second, you can hear it maybe. If it oscillates back and forth 20,000 times, you can hear it. So this would be a very, very low frequency note, something rumbling, like a truck going by. And this would be a super high frequency, like a mosquito, or even much higher than a mosquito. Now, as you get older, unfortunately I'm over 40, as you get older, your ability to hear up around 20,000. I can't hear at 20,000. I can't even hear like 15,000 hertz. Any note that high, it's beyond my hearing range, unfortunately. Too much loud rock and roll music, apparently. Now, different animals have different frequency ranges. A frog can hear between 100 and 3,000 hertz. So if I sing above 3,000 hertz, the frog can't hear it, which is probably good. This is my old dog, Moose. Dogs, as you may know, have really high, there's a thing called dog whistle. And if you blow a dog whistle, humans can't hear it. It's above 20,000, but dogs can. So different animals have different frequencies they can hear. Dolphins have super high frequency. Now, in class, we normally do a little activity where we have a sound test, where we played notes from 20 up to 20,000. Usually I lose my hearing around 15, but some kids can actually hear much higher. So it's kind of an interesting activity. And if you get a hearing test, probably you got a hearing test and you're a freshman, that's what they check is how well you can hear different frequencies. So we went into the lab, we did a lab where, again, we used a microphone to look at these. The microphone records the frequency of different notes, and we took a look at them, and we calculated. So again, if we make a sound with a speaker or with a tuning fork that has a certain compressions or rarefactions travels to your ear, we looked at the pressure versus time graph on the computer, and we counted number of peaks per second and got the frequency, and we compared it to the, we used tuning forks, and the tuning forks have the actual frequency stamped on the side. And we went into the computer and looked at the frequency and tried to compare. We get really good numbers. So we got some lab data, and we got, you know, the microphones do a great job of being able to figure out that frequency. Now, the other thing I'd just like to briefly talk about is you can tell when a person's talking versus a flute or a violin or a gong or a tuning fork. Although these things have the exact same frequency, they go up and down the same number of times per second, but they look different because they sound different. So a tuning fork has a nice pure tone, whereas a gong has a rough tone. The violin may have the exact same frequency, but you can distinguish. So when you hear even a friend talking, your friend's voice has a very distinct signature. So again, a tuning fork, a flute, and a clarinet all have the exact same frequency, but they have different tonal qualities that you know that, hey, that's a flute, that's a clarinet, that's my friend's voice. So that's the only thing we're getting at, is the note is a frequency, but each instrument has a different tonal quality. The other thing, and we're not going to spend a lot of time on this, but wave interference, I think Mr. Deere talked about this. When you have waves lined up, the peaks add up vectorially to make a bigger wave. That's constructive. And you also have, if waves match up perfectly to cancel, if the +1 and the -1 add up and make it smaller, we call it destructive. So Mr. Deaver went into something about beats and noise-canceling headphones. A lot of kids nowadays have noise-canceling headphones. So if you have some background noise, like a plane or a train or a bus engine or something, the microphone, the headphones themselves actually make a anti-noise. They actually listen for the frequency of the noise, and then they produce an anti-noise that cancels. So if you have a set of those and you listen to them, you use them on airplanes, for example, they're awesome. But it's using the basic idea we studied back in the wave chapter. We're not going to get into this in great detail. It's something called beats. I'm going to skip over this stuff. It's not super important. The other thing I just briefly mentioned is if we said pitch is frequency, so if this characteristic called frequency corresponds to something you hear as pitch, the amplitude of the wave or the height of the wave corresponds to its loudness. So for example, here we have two waves that have the exact same amplitude. These waves have the same height off the x-axis, but they have different frequencies. So somebody would hear this as a high note, and then somebody would hear this as a low note, but they'd have the same loudness. Now over here we have two waves that have the exact same frequency, so the exact same note. Somebody might be singing here, ah, and here, ah. So it's the same note, but they have different loudnesses, and the amplitude of the height of the wave determines the loudness. Now we do not go into great detail in the calculations. You've probably heard the decibel scale. Some things are very, very soft. Whispering is 20 decibels, and normal conversation is 60, and a truck is 80, and an airplane is 120. This is just a scale we use to describe how loud or the amplitude of the sound wave. And again, you don't need to worry about this. I'll skip along here. This is the loudest football field out in Kansas City. They got the decibels up to 142, which is louder than an airplane, which is amazing. Again, I'm going to skip over most of this. So we don't do the calculations. It's kind of a mess. Likewise, standing waves, I'm going to skip this for the time being. I think I want to get to Doppler effect. So this stuff you don't need to know. Some interesting demos, but stuff that's not crucial to you. And again, I apologize. This video is going to be a little longer, so I'm going to skip ahead and stop and take a break. So the last thing we really want you to know, and I needed to talk about that frequency stuff, the last thing we need you to know is something called the Doppler effect. So the Doppler effect, it can be a little tricky here, so just bear with me for a second. To understand the Doppler effect, you've heard it before. If you stand next to the road and you hear a car go by, you'll hear a you'll hear the actual frequency or the pitch change as the car drives by you, or if you've heard an ambulance go by. So this Doppler effect is caused by motion. And so the way I teach this is I think about, here's a bug sitting on the water. So imagine the bug sitting on the water, and the bug's going to bounce up and down. So I'm going to take a bug and I'm going to put him on the water from the side view. And the bug's going to bounce up and down at some frequency. So he's my way. Now when he does that, it's going to create waves up and down. So if I put rubber ducky over here, and I put rubber ducky over here, these two rubber duckies are going to see these waves propagate out on each side at the exact same speed. And rubber ducky is going to start oscillating up and down at the exact same frequency. From the top view, if I was standing above the bug and looking down, the bug bouncing up and down would make a bunch of ripples, kind of like dropping a rock into the pond. And it would make a bunch of ripples. But because the bug's not moving, they'd have perfect symmetry. The waves would propagate out in all directions at a fixed speed. So if I put rubber ducky here and I put rubber ducky here, these rubber duckies would bounce up and down at the exact same frequency of the bug. Now that's not the Doppler effect, but that helps to explain the Doppler effect. Now I'm going to do the exact same thing. I'm going to draw the bug here on the ground, on the water, but now the bug's going to bounce up and down, but he's going to move towards rubber ducky number 2. So the bug's going to travel this way as he bounces. And what's going to happen is, and you may or may not be able to visualize this, but I'll show you some animations in a second. What's going to happen is the concentric circles get skewed one way. Because he's moving towards rubber ducky number 2, the waves get more closely packed together on this side and they spread out on the other side. So if that makes sense to you, that's great. But if it doesn't, don't worry about it. You don't have to totally get this to understand how to do the problems. So what's basically going to happen is rubber ducky number 2 is going to vibrate up and down at a high frequency, where rubber ducky number 1, the waves are going to hit him less often. So he'll move up and down more slowly. And again, I'll show you some animations to show you this. So this is the initial definition of the Doppler effect, which says the frequency of a wave changes from an observer due to motion. And again, I'll give you a more formal definition in a second. Now, you've heard of Doppler with Doppler radar on the news all the time. They brag about how good their Doppler radar is, even though their weather forecasts are horrible. But, so you've seen this before. I'm going to click ahead. So one thing to pay attention to is the Doppler effect can be caused by the source, the bug moving up and down, the bug's moving, or the observer can move, and I'll explain that in just a second. Now, this is one animation to make it clear. And again, I apologize. This video is going to be a little long, so you may have to stop and take a little break. But this is a simulation of the Doppler effect. If I click on here, it's going to here's a jet airplane. And the jet airplane is making the sound of its engine. And the airplane's not moving, so the sound travels out everywhere. So if you're over here, the sound waves will hit you at a certain frequency. You'll hear a note. If I'm over here, the sound waves will hit you at the same frequency. I'll hear the same note. And if I'm over here, I'll have the same thing. The waves are traveling at the same speed. Now I'm going to do that again, but now I'm going to have the airplane move. So if the airplane's moving, again, this is the bug. If you're sitting here, the waves will hit you more often. So it'll be a higher frequency, so you hear the note higher. If you're on this side, because the airplane's moving away, the waves will hit less often, so you hear a lower note. And this depends on how fast we're moving. If we're moving 37% the speed of sound, then it's a slight shift. If I move at a higher speed, let's say 75% the speed of sound, then they'll bunch up even more. So somebody over here is going to get boom, 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 boom. No, over here they'll get boom, boom, boom. So again, the frequency changes because the source of the sound wave is moving. There's something called Mach 1. If a pilot flies faster than the speed of sound, they're actually outrunning the sound waves. So the pilot up here in front of the airplane actually can't even hear the airplane. So this is called Mach 1, or if you travel faster than the speed of sound. Okay, so that's to introduce the idea behind the Doppler effect, to show you visually what it looks like. So the faster you go, the bigger the shift. I'm going to skip that. Now, so this is the basic idea that if you change the frequency, then you're changing the pitch. So it goes back to what we talked about before. So as the frequency increases, the pitching increases. And I have a couple examples here. So here's the very typical example. So we'll do that again, but if you listen closely, you'll hear, go back, you'll hear that's the natural frequency of the horn. And as it comes closer to you, the frequency you hear is higher than the actual frequency of the horn. So you hear the pitch being, really high, and when he goes by, the frequency will drop, the note will drop. So high pitch, coming towards you, and lower pitch as it goes away. So that illustration is the Doppler effect. Okay, and the same thing happens with trains and all these other things. So it's the familiar, so high frequency, low frequency. Now this animation is really good, and it's going to be about 3 or 4 minutes long, but it's a video that summarizes everything. And Doppler effect is crucial that you understand conceptually what's happening. So if this makes sense to you, then you're in great shape.
Smart dogs can't stop distracted
First
driving,
commercial.
but your smartphone can. The Doppler effect. In Sheldon's words, it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does that mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means a redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and an indication that the Earth might get very lonely in the distant future.
Okay, so that's a quick summary of what the Doppler effect is, and hopefully that made sense. And the reason why it's important is that now I'm going to show you the math for the calculations, how to actually do this, to calculate Doppler effect type problems. So again, if you get the basic concept, it's important. So at the end of the video, the guy's talking about this is the proof the universe is expanding. I'm sure you've heard of the Big Bang. And the idea is that astronomers look out in space and everything is redshifted. All the stars appear to be moving away from us because they can look at the light and see it's been shifted to the red. So it's one of the big proofs of the Big Bang theory. And you could actually do this. It'd be very difficult to do, but if you had a friend wearing a yellow shirt and he ran towards you, if he ran towards you, his shirt would actually turn blue. If he ran away from you, his shirt would actually turn red. Now, you'd have to be moving really, really fast. So you don't notice this. If you go to the beach and your friend's walking on the beach, you don't see a difference in the shirt color because it would change tiny, but it would be minute. This is also in the weather. They use Doppler shifting to figure out if there's a tornado. So if the air is blowing towards you, we say it's blue shifted. If the air is moving away, it's red shifted. And if we see blue and red air, kind of, and then we can interpret there's going to be rotation. We have air blowing 2 different directions, which suggests rotation. This is how they look for tornadoes on radar. This also, if you've ever had the pleasure of getting a ticket, the police officer will send that away from his radar gun, hit your car, and if your car is speeding towards him, the wave comes back at a higher frequency, and they can do a calculation between the frequency it went out at and the frequency it came back to figure out the speed. So if you see one of these radar guns, usually by the time you see it, it's too late. You've gotten your ticket, so drive the speed limit, especially in Monroe. Same thing in baseball. Baseball pitchers, the coach usually has a speed gun to measure the speed of the pitcher. So this has a main application. Same thing at airports. They have Doppler radar to look for downdrafts. Fast-moving areas could cause a problem to airplanes. Now, the Doppler equation. This is the tricky part. So again, take your time. If you look at this picture, I'm going to explain, the typical ambulance or car coming towards you or away from you. And there's a mathematical equation, and I'll walk you through an example or two, and then you can try the homework. So here's the picture that's most important. Here's a source in an ambulance that makes a frequency. A siren makes a frequency, and that's some number. So here's the source. Now, a listener standing on this side, because the ambulance coming towards him, will hear it at a higher frequency. And a person over here listening, because they're moving away from that person, would hear it at a lower frequency. So it's really crucial that you understand the relationship between the frequency of the source and the frequency of the listener. And because this listener is on this side, this person will hear at a higher frequency, so the listener's frequency will be higher, but this listener over here will be lower than the source. So this statement, this inequality, is crucial when you're doing these problems. You almost can't get Doppler problems wrong because you'll know what the answer should be. Now, the equation's a little scary when you first see it. It says the ratio of the frequencies, and I always put the listener stuff on top. You'll see why. So the ratio of the frequency the listener hears versus what is actually made equals V plus or minus VL over V plus or minus VS. And it looks a little daunting, especially this plus or minus thing, but V is going to be the speed of sound. And you'll see an example. So these are the frequencies of the listener and the source, what the source actually makes and what the listener hears. This V will be the speed of sound through air. Now remember, usually V is going to equal 343 because we're assuming temperature is 20 degrees. So at 20. These velocities will be how fast is the listener moving or how fast is the source moving. And one of these will always be zero. We'll always have one thing stationary and one thing moving. So you'll see what I'm talking about in just a moment. So this equation is the one you want to jot down. We'll talk about the signs in a second. So let's understand the basic idea. And again, I'm going back to this again because it's kind of crucial. So in this case, if either the source is moving towards the listener or the listener is moving towards the source, so if they're coming together or towards each other, then the listener will hear it at a higher frequency. And that makes sense because the waves are punched up. So that inequality is important. If it's the other way around, if the source is moving away from the person or the person is moving away from the source, if they're moving away, then the frequency will be lower for the listener. So the frequency of the listener hears is less. And again, this is crucial. So let's do a quick example. I'm going to walk you through the steps. So the first thing I normally do is I draw a picture. It says a horn of a car. So the car is moving. The car is moving at 30. So I'm going to draw a car. And the way I do is I put the frequencies above and I put the velocities below. Here's a listener over here. So this is the source. This is the listener. Now, the car is moving towards the person. Not towards. So I say I do the velocities below. So I'll say the velocity of the source is 30. The listener is not moving, and remember, I'm always going to have one thing is not moving, so that's 0. The frequency of the horn, the frequency of the source, is going to be 500 hertz, 500 cycles per second, and the frequency of the listener is going to be question mark. So the nice thing about this is that if you take your time and draw the picture and label everything and think about it, you can then write the inequality and then solve the equation. Now, there's 2 methods of solving the equation. One method is called guess and check. You just say, I have no idea. I'm going to put a sign in either plus or minus. Use your calculator, calculate the value. And if the answer comes out and agrees with the inequality, then you're good. If the answer comes out and makes no sense, it means you've picked the sign incorrectly. So let me show you what I mean by that. So I'm going to scroll down a little bit and see if we can fit this in here. So because we're looking for the frequency of the listener, I'm going to set up the inequality with the L's on top. So I'm going to say FLFS equals V plus or minus VL over V plus or minus VS. Now notice that this equals 0, so I'm going to get rid of that. I don't have to worry about it. So I don't have to worry about the plus or minus sign on top. Now, again, the other thing, the most important thing is the inequality. So because the source is going towards the listener, the frequency the listener hears has got to be bigger than the frequency of the source. The person's going to hear the pitch at a higher value. So this inequality is crucial. It's based on what we talked about in the previous couple slides. Now, if that's the case, I'm going to take this equation and rewrite it. Go back to my black pen. I'm going to say, all I'm going to do is bring, because I'm looking for FL, I'm going to bring the FS up. So it's going to turn to FL equals FS times V over V plus or minus VS. So the reason why I'm doing this is it's a lot easier for me to see this. If I want the FL to be bigger than FS, FL equals FS. Now, FL will be bigger than FS if this thing in the circle is greater than 1. Now again, you don't have to know that. What you could do is you could just say, hey, I'm going to pick a sign plus or minus and then do the calculation. And if my answer comes up with my FL bigger than the FS, then I know I'm right. But some students looking at go, hey, for the FL to be bigger than FS, I'm going to multiply FS by something. And if this thing is larger than 1, then it will come out be that way. Let me scroll down a little further. Now, to get this thing bigger than 1, I kind of cheat. I go 7 over 7 plus 2. I just make up numbers, or 7 over 7 minus 2. Which one of these signs will create a number bigger than 1? Well, I think you can see that if I have a negative on the bottom, I'll have 7 over 5, and that's bigger than 1. If I have 7 over 9, that's less than 1. So some kids do this by just thinking about it. They say, oh, it's got to be a negative for this to be true, to make this true. So it must be FL equals FS over V minus VS. Now that should yield a number of FL bigger than 500, because FS is 500. And if I get something bigger than 500, I know it's correct. And sure enough, if I do this, I'm going to get 5. I'm going to put numbers in now. Remember, V is the velocity of sound at the temperature, and we'll assume it's 20. I'm going to say minus, and the velocity is 30. So I can see right now that, and I apologize, I don't know what this number is, but I don't have my calculator with me. But if you look at this, this is definitely bigger than 1. And so it's going to come out to be like 560 or something like that. You'll have to check that. I don't know. But I know it's bigger. So when I get this number, I'm going to say, yes, met that condition. So this last step is important. Write the inequality, do the calculation, get your number, and go back and look at your inequality. If you have picked the sign correctly, you'll have this to be a true statement. Now, a lot of kids do guess and check, so don't worry about the whole conversation about bigger than 1 and negative. Probably half my kids, at least half the kids go, I have no idea. They just pick a sign. They do the calculation. If they picked wrong, this inequality won't work. And then they go back and they change the sign. And if it does come out correct, then they know they've picked correctly. So Doppler problems, you really can't get them wrong. Now, I'm not going to do them more because Mr. Deaver attached a homework set on Doppler. And again, the answers are in parentheses. So if you do a couple of these, you'll get the idea. He gave like 5 or 6, but if you do 1 or 2, they're all kind of the same. I really, really strongly recommend now you draw the picture like I did. I put the frequencies above. I think about who's moving. Is it the source or the listener? I write the velocities below, and then I write my inequality. Then I just plug in the numbers. So if you have any questions on it, give us a call. Again, I apologize. I know this is a really long video, but hopefully you can break it into little pieces. We hope you're doing well. Get well. Hope to see you back on school on Monday. Hopefully Massey has school on Monday, or Tuesday. I guess you'll be back, hopefully. Anyway, do well. Enjoy the weekend, and we'll see you soon. All right, Gabby, thanks.